Thank you all very much for joining us today. During this presentation, we're going to tell you about Arbiter, an open source cloud native framework for drop-in video conferencing. Before we get into it, quick introductions. My name is Jay. I'm a software engineer located in Brooklyn and one member of the Arbiter team. Tyler?
Yeah, my name is Tyler Frye, software engineer out of Tampa Bay, Florida.
Stephen? All right. So 4 sections to today's presentation. I'll kick things off with an introduction to set the stage and then hand it over to Stephen and Tyler to talk about building Arbiter and scaling Arbiter. So what is the problem that inspired us to build Arbiter? Well, the problem is that video conferencing is now a fundamental requirement for many, many web applications. This means many web developers are in the position of needing to add video conferencing capabilities to an existing web application. And so for a developer in this situation, there's broadly 2 approaches to choose from. First, they could choose to purchase a commercial solution, but this is costly and leads to vendor lock-in. The other approach is a more do-it-yourself approach. The problem here is this requires substantial developer time and diverts attention from core application features. We surveyed existing solutions and grouped them into 3 buckets. So commercial products, as we mentioned, are on the left. They're a costly option. And here the cost is fees paid to a company. Now, some developers are going to be very happy to pay these fees because commercial products do a great job of abstracting complexity and require little developer effort. These products are easy to integrate and easy to deploy because the developer does not self-host the application on their own infrastructure. Instead, the application runs on the company's managed infrastructure. On the right-hand side, a true DIY approach in which a developer builds on low-level open source libraries is also costly. In this case, the source of the cost is developer effort. These libraries are flexible, but require substantial developer effort. So this is not an easy to integrate option. The DIY approach does allow the developer to self-host an application, but this requires additional effort from the developer to design and deploy scalable infrastructure. So this option is not easy to deploy. The in-between solutions are full-featured open source projects specifically designed for video conferencing applications. This is relatively low cost. Like commercial products, these are easy to integrate, but like a do-it-yourself approach, the developer must self-host the application, and this is not an easy to deploy option. Last thing to note here is that commercial solutions and the in-betweens include advanced video features. So here we're thinking about things like breakout rooms, customized backgrounds, and so forth, which may not be required for all applications. When we looked at these solutions, we saw a gap, and to bridge this gap, we built Arbiter. Arbiter is designed to be easy to integrate, self-hosted, but also easy to deploy. To accomplish this, Arbiter includes a command line interface. A single deploy command spins up the Arbiter video conferencing application and a scalable cloud architecture in the developer's own Amazon Web Services environment. Arbiter also includes a React SDK. With a couple lines of code, the Arbiter video conferencing application integrates into an existing web application. So who should use Arbiter? Arbiter is a good fit for teams who are looking for a lower cost solution because it is easy to integrate, easy to deploy, and has no commercial product fees. For teams that are willing and able to host an application in their own Amazon Web Services environment, who are looking for video conferencing solution that has support for many rooms, each with unique URLs, and for a solution that offers basic video conferencing features. Arbiter does not support all of the advanced video conferencing features of a commercial solution, but for many applications, these are not required, and Arbiter will be a good fit. So let's turn now to some of the considerations we faced when building Arbiter. One of our first questions was, which streaming media protocol is best for the Arbiter use case? A streaming media protocol is a set of rules that governs how data is transferred between devices. For Arbiter, we identified three critical factors. First is latency. Near real-time latency, under 1 second, is required to produce a user experience that feels like a face-to-face conversation. We also decided browser support and encryption were requirements. We chose WebRTC as the streaming media protocol because it delivers 500 millisecond latency, wide browser support, and also offers end-to-end encryption. So what is WebRTC? It's an open specification for streaming media, audio, and video between peers. It uses User Datagram Protocol, UDP, at the transport layer. UDP is a connectionless protocol that prioritizes speed of data transfer over assurances of reliability provided by its alternative transfer control protocol. UDP enables WebRTC to deliver minimum latency. WebRTC also provides an API to access and manage browser media streams. So next, we had to learn, how is a WebRTC connection established? This brings us to negotiation. Negotiation is a multi-step handshake process that establishes a WebRTC connection between peers. The first important point to note is that peers are going to need to relay messages through what's called a signaling server. In this example, Mary and Sam want to negotiate a WebRTC connection, but they have no direct connection to each other and cannot communicate. So instead, both connect to a signal server sitting in between them. The signal server relays messages called signals from one peer to the other. During negotiation, call parameters are agreed upon using Session Description Protocol, SDP. Parameters include the types of streams, audio, video, number of streams, codecs to be used, many other parameters. Also, during negotiation, the lowest latency IP imports are determined using Internet Connectivity Establishment, or ICE. Each peer will send many ICE candidates containing IP and other networking information. Many signals move across in each direction during the course of negotiation. The Arbiter signaling server is implemented as a WebSocket server. WebSockets enable full duplex bidirectional communication, which is ideal for negotiation. When peers attempt to connect over the internet, there are obstacles between them. So how does WebRTC handle these? The first main obstacle to consider is that nearly always peers do not know their public IP address. Why is this? It's because most computers sit behind a router. A router is a network address translation device, a NAT device. A NAT device holds a public IP import that maps to the computer in the private network. The computer does not have direct access to that IP import. And why is this a problem? Because as we just saw, each peer must share its IP address during negotiation. The second main problem is that sometimes security settings of these network devices are restrictive and prevent a direct peer-to-peer connection. This is particularly true of what's called symmetric NAT. So to handle the first problem, WebRTC requires a STUN server. STUN stands for Session Traversal Utilities for NAT. The way it works is a peer sends a request to the STUN server. Server sends a response that contains the computer's public IP import. To solve the second obstacle, WebRTC requires a turn server. The turn stands for traversal using relays around NAT. The turn server sits between the two peers. Each peer sends streams to the turn server, and the turn server in turn relays the streams between the two computers. To build Arbiter, we needed to implement stun and turn servers. And our last major consideration was, what network topology would we use? WebRTC supports many different network topologies. The main categories are mesh and client server. In the mesh topology, also known as a peer-to-peer topology, each client connects to every other client. The advantages of a mesh topology are it is simple and low cost because there is no server involved. However, it supports only very small call sizes. This is because the number of connections scales exponentially as the call size grows. And this means that resource needs for each participant grows and quickly exceeds their capacity. For Arbiter, we chose a client-server topology. The advantage here is reduced resource requirements for the client. Each client connects only to the server, and total connections scale linearly with call participants. This topology is more complex and more costly due to the presence of a server, but this is a necessary trade-off to support the large call sizes required for video conferencing. Within the broad category of client-server, there are two main subtypes: the multi-point control unit, MCU, and selective forwarding unit, SFU. In the MCU topology, the server receives streams from each client and produces composite streams for each client. This minimizes client resource needs. Each client has one upstream and one downstream. However, the server takes on a very high computational load and becomes quite expensive to operate. In the SFU topology, the server receives streams from all clients, but instead of combining them, it forwards them instead. The advantage is a much lower computational burden on the server and lower cost to operate. The trade-off is that clients maintain n-1 downstreams. But each client still has only one upstream, as in the MCU topology, and it's upload bandwidth that is typically the bottleneck. We selected SFU topology for Arbiter because the server is much less expensive to operate than MCU, and it does not overburden clients. So to summarize here, we selected WebRTC in large part due to its very low latency. We needed to build a signaling server and also implement stun and turn servers. And we selected an SFU topology for its ability to support large call sizes cost efficiently. So I'll turn things over to Stephen next.
Great, thank you, Jay. So in the second part, I'm going to talk about how we build Arbiter using the information that Jay talked about in order to create this from the ground up. In order to explain how we built Arbiter, I'm going to talk about it through the lens of some of the major challenges that we faced. I'm going to walk you through those challenges and how they work in the scope of actually building our application. The first challenge is, what is an appropriate architectural design for an SFU? Which means, like, what does an SFU actually have to accomplish and how does it work? And secondly, as Jay said, signaling is really important. It can prove really difficult as users scale. And so making signals reliable was something that we had to solve in order to make Arbiter work the way that we wanted to accommodate many users across many rooms. First, let's talk about designing the SFU. So kind of surprisingly, research turned up very little information about what an SFU actually is. There were a large number of examples and ideas across many different sources that included things as simple as the basic diagram that Jay showed you of a server sending and receiving streams, and all the way to a microservice-based architecture with multiple servers communicating with each other. And because there was no clear agreed upon definition based on the fact that this idea of an SFU with WebRTC is a relatively new idea, we took the one piece of consistent info that we had, which was the SFU forward streams. So we took a really naive approach to this idea of it forward streams. Based on our peer-to-peer experimentation, we learned how WebRTC connections can be established, what that negotiation process looks like. It's a little bit different with a server compared to a peer-to-peer framework, though. With a central server, in our case, the SFU, is actually going to create individual WebRTC connections with each peer. So our first idea was, in order to forward streams, what if we simply added each user's upstream media stream information to another user's existing connection and send it downstream? So looking at this diagram, the first idea is Sam connects to the server. Sam negotiates, sends an offer and receives an answer, and sends his media stream to the SFU. Then Mary also connects in the exact same way. And then the idea is simply, if we forward Sam's media stream to Mary and Mary's to Sam, they could both have each other's information, and this would be stream forwarding. However, there was a significant problem with this rudimentary approach: renegotiation. So, looking at this diagram, we have Sam and Mary again, but this time we're looking at a model of what the SFU and the clients kind of look like. So we have Sam and Mary on their computers, and then in the center, in the yellow box, we have the SFU. The arrows from Sam and Mary represent a WebRTC connection being established with the SFU, and then the individual balls represent their media stream data. So the problem that we had was, if I take, let's say, Sam's pink media stream data through the SFU and add it to the existing connection for Mary, that's a problem. If you remember from what Jay was talking about, when you negotiate a WebRTC connection, it includes something called an SDP, or Session Description Protocol. And that SDP basically says, hey, I'm going to be sending you this media, this video, and this audio, and expect it in this format. Now, all of a sudden, you've introduced new media, right? There's a new video, there's a new audio, and they might have different formats. This causes the connection to break because it wasn't part of the original contract negotiated to make the connection happen in the first place. As a result, we needed to find a new way to implement sending streams to avoid this problem of renegotiation. So to address this, we devised a strategy of producer and consumer connections. So the idea is, rather than worrying about renegotiation or the logic associated with that, we don't want to interrupt the user experience and be forced to renegotiate and break streams. So what we're actually going to do is create a new connection for each media downstream. So notice this diagram, unlike the previous one, doesn't simply forward the streams, but the SFU is actually making an offer and negotiating a new connection with each of the peers so that it can then forward that media data to each peer. So let's return to the example from before, this time with the producer and consumer logic. So in the diagram on the left, now Sam, Mary, and the SFU have a specific producer WebRTC upstreams and specific consumer WebRTC downstreams. One upstream is always maintained from each client to the server, and n downstream connections that represents the number of other users in the call. This avoids the process of renegotiation entirely. The logic holds as more peers are added as well. Let's say, for example, we wanted to add Pippin to our call. Well, when Pippin joins the call, he negotiates his upstream connection with the SFU, which is then a new negotiated WebRTC connection with the existing callers, Sam and Mary. Then Pippin can have Sam and Mary's media streams negotiated with him individually as well. Each arrow is a distinct WebRTC connection in this diagram. So in all, this means that the SFU is negotiating 9 separate WebRTC connections to accommodate 3 callers. While this is a lot of data to be sent, it's still significantly less than it would be with a mesh topology, allowing the call to accommodate many more users. Seeing how the SFU needs to create and maintain so many connections in different directions, the logic is really important of how those connections are actually negotiated and maintained. In general, we want to avoid issues when making and accepting offers. With a peer-to-peer WebRTC topology, the order of negotiation is completely variable because the order in which peers joins is unpredictable. There's always the question of who starts the conversation. Like in real life, if both parties are shouting over each other to make offers, the connection doesn't get made. To address this, generally speaking, WebRTC uses what we call polite peers, which are peers who are always waiting for offers to be made to them, and impolite peers, which are peers who are not ever going to be waiting for an offer and are going to be making offers. If the signaling logic isn't consistent and you don't have polite and impolite peers, it can lead to no connections or renegotiation, which again is something we really wanted to avoid. So to streamline this with an SFU, we use the idea that the SFU is a consistent presence in all of these calls. The order of the peers is still unpredictable, but what is predictable is that the SFU is always there listening for new peers. As a result, the SFU can be polite as it listens for new clients to join, which avoids any issues involving negotiation. Similarly, the client is polite for the downstream connections. So the logic is reversed, where this time what's consistent is the SFU is aware of new peers joining the call. As a result, it will be the one making offers specifically for downstream connections. As a result, we'll create an offer to negotiate new consumer connections, which avoids issues with negotiation. After solving these problems, we accomplished some of Arbiter's main goals. Most importantly, we had a functional SFU, which was able to send and receive user signals to many peers in the call. We also had reliable signaling logic, which would allow for avoiding renegotiation or any issues during that process. And we could support real-time multi-peer conferencing. But we still had some challenges. First of all, we learned that conference calls take a lot of network bandwidth and computer resources, CPU and memory. So without buying very expensive servers, generally speaking, a single server could accommodate one room. At the time, our server was running on a monolith, so therefore we were limited to only one room, even if we had many users in that room. Additionally, it was expensive to operate because all of the servers were always on, because they always needed to be listening for callers to join. That made this prototype very expensive, and it was also very inflexible. Because it was on a monolith, if we wanted to add another room, we would have to spin up a whole new server cluster, a second monolith, if you will, to accommodate that. As a result, we decided to redesign Arbiter's architecture from the ground up. I'm going to talk to you a little bit about what you get when you spin up Arbiter and deploy it. And then Tyler's going to talk to you about how we changed it to accommodate for some of these challenges. So first of all, Arbiter now consists of a command line interface, which is an NPM package you can install and simply run Arbiter deploy to get all of Arbiter's cloud-based infrastructure available to you within minutes, as well as a React SDK, which you can also download, put into your app with a single React component, and within minutes, you'll have it integrated into every page of your application that has the component integrated into it. Arbiter achieves many rooms through URL-based routing. So every, again, unique URL gives you a different room, which allows Arbiter to accomplish its main use case. Now, Tyler's going to talk to you about how we actually went about scaling this to accommodate our backend infrastructure to be able to make this possible.
Thanks, Stephen. So in this section, I'm going to discuss the need to move to a cloud-based architecture to facilitate that kind of scaling, the problems we encountered in doing so, how we solved the problems, and the final architecture of Arbiter. In our prototype of Arbiter, we had multiple Node.js Express servers running on a single machine in a monolith architecture. We discovered, due to network hardware limitations, that we needed to scale the SFU horizontally in order to support many users across many rooms, with SFUs and rooms having a one-to-one relationship. To promote this type of scaling, we needed to move Arbiter away from a monolith and towards a cloud-based microservice architecture. For this, we chose Amazon Web Services, or AWS. In our initial move to the cloud, we utilized AWS EC2, or Elastic Compute Cloud, a service to launch and manage virtual servers. We used EC2 to host our three main pieces of infrastructure in the cloud: the Stun server, the signaling server, and the SFU. We quickly noticed that this was a suboptimal solution for our use case, as it presented three major problems. EC2 instances are always on, increasing the overall cost. They're difficult to scale up automatically, and they take a significant amount of time to spin up. To promote cost efficiency as well as speed and ease of scaling, we needed to think of alternative solutions for each stack. So Arbiter consists of 4 major stacks: the HTTP API gateway to manage rooms, the WebSocket API gateway to facilitate the exchange of messages between client and SFU in that signaling process that we've discussed, the stun-turn stack for IP discovery and media relay, and then the centerpiece, the SFU cluster, which handles the forwarding of audio and video streams between clients. Finally, to tie it all together, we have the Arbiter SDK, which consists of a drop-in React component to make it easy for developers to integrate into their own applications. For the signaling stack, we chose to use the AWS WebSocket API gateway, along with AWS Lambda functions and DynamoDB, a NoSQL database to store session data. The WebSocket API allows for a persistent WebSocket connection and near real-time bidirectional communication between the client and the gateway. Upon receiving a request, the WebSocket API gateway will forward the request to the provided integrations, which in our case are AWS Lambdas tied to that DynamoDB. Lambda functions are serverless functions that run in the cloud in response to some trigger, and only run when they're invoked. Since signaling happens infrequently, having an always-on server is not optimal. By using Lambdas, the code only runs when signaling needs to happen, thus reducing the cost for developers using Arbiter and solving our first problem of EC2 instances sitting idle a majority of the time. The signaling stack is composed of 4 key Lambdas: connect and disconnect, which add and remove socket connections to and from the DynamoDB; identify, which allows clients and SFUs to store metadata about themselves for their session; and handshake, which actually facilitates negotiation of session descriptions and ICE candidates between clients and SFUs, which are necessary to establish a WebRTC connection. Recall Jay and Steven's walkthrough of this signaling process from earlier. With this architecture, we were able to meet our goals of scalability and cost efficiency, as Lambdas allow for a high level of concurrency and the Lambdas only run when needed. Now that we have a scalable cloud solution for the signaling process, we need to ensure that clients can connect regardless of network obstacles. For the stun-turn stack, we use CoTurn, an open source and widely used solution for addressing issues surrounding NAT by implementing stun and turn. Recall from earlier that stun allows for public IP discovery behind NAT devices such as routers, and turn acts as a trusted relay server for clients to connect to in case they're behind a restrictive NAT. We realized that as the number of users grows, a single server running CoTurn would not be enough, and we needed to automatically horizontally scale to meet demand. For this, we chose to containerize CoTurn using Docker and deploy those containers with AWS, ECS, and Fargate. We also implemented a network load balancer. ECS, or Elastic Container Service, is a fully managed container orchestration service which enables deployment, management, and scaling of Docker containers on a cluster. AWS Fargate is a serverless compute engine for those containers, which removes the need to manually manage servers and clusters and allows you to quickly and easily spin up new containers within that Elastic Container Service. The network load balancer allows for even distribution of requests across many containers. With these architecture choices, Arbiter is able to automatically spin up new CoTurn containers to handle increased load, and it solves the problem of long spin-up time with EC2, as ECS containers spin up much more quickly. ECS containers also allow for more efficient resource utilization and elasticity, which solves our problem of cost efficiency. The final problem with the CoTurn stack is that once a user connects to a CoTurn instance, they must communicate with the same instance on all subsequent requests, or connections can fail. We solve this by using a network load balancer and enabling sticky sessions, so that user would always be directed to the same CoTurn instance. For the selective forwarding unit, as mentioned earlier, we realized that due to network and hardware limitations, we needed a single SFU for each room. We considered the same problems as the CoTurn stack, speed and ease of scaling, as well as cost efficiency. This led to a near identical solution as the stun-turn stack, containerizing the SFU application code using Docker, and utilizing Amazon Elastic Container Service with Fargate. This leads us to the same benefits. It allows Arbiter to quickly spin up rooms as needed, as well as more efficient resource utilization, reducing the overall cost. The final problem with the SFU stack is how rooms are managed. Load balancing is not arbitrary as it is with the stun-turn stack, as users joining a room need to connect exclusively to other users in that room. You wouldn't want to join a call and be met by a totally random group of strangers that you did not intend to video call with. Cue the HTTP API stack. For this, we chose to use AWS HTTP API Gateway alongside AWS Lambdas and the same DynamoDB that we discussed earlier. Similar to the WebSocket gateway, the HTTP API gateway forwards requests to the provided Lambda integrations, but instead of using a persistent WebSocket connection, it uses the standard HTTP request response cycle. To actually handle the management of rooms, we created 3 routes. Claim room, a patch request that allows users to assign their unique URL to any unclaimed SFU. Get room ID, a GET request that attempts to retrieve the room ID associated with the provided URL. And create room, a post request that communicates with ECS in order to spin up a new SFU container. Spinning up a container takes a relatively short amount of time, but for an end user, a minute can seem like a really long time. Thus, to improve the overall end user experience, in the Arbiter CLI, we allow developers to have any number of SFUs sit in an idle and unclaimed state as a buffer, ready to be instantaneously claimed by the end user. As such, whenever a room is claimed by the end user, the create room route is also hit to maintain that SFU buffer. This very minor increase in cost of having idle containers is a trade-off to promote a responsive and seamless experience for the end user. Now we have all of our backend infrastructure in place. The SFU cluster allows for forwarding of media streams. The signaling stack allows for communication between clients and SFUs to establish WebRTC connections. The stun-turn stack allows for traversal over network obstacles. And the API stack allows for the management of rooms. But how do we tie it all together so that an existing front-end application can access Arbiter? Well, implementing Arbiter into the front-end application is a really simple process. Once all of the infrastructure is deployed to AWS, the Arbiter CLI provides an environment file containing the endpoints for both the signaling stack and the HTTP API stack. Once the developer has placed this environment file in their React application, all they must do is import the Arbiter SDK, a simple npm package, and use the Arbiter component in their application. And this component handles all of the heavy lifting of connection management, front-end rendering, permissions of video streams, and so forth. With the front and back ends both in place, Arbiter accomplishes the goals we initially set out to reach. We have abstracted away the back-end complexity of building a WebRTC infrastructure from scratch. We have provided a command line interface for one command deployment of all of the backend infrastructure, and we have allowed a developer to drop in a React component to easily add video conferencing into their application. With all of this, a developer can now go from having a basic application to having self-hosted video conferencing capabilities in their application in a matter of minutes. And that's Arbiter, an open source, cloud-native framework for drop-in video conferencing. And now I'll hand it back over to Jay for a quick Q&A.
Right. Thank you, Tyler. Thank you, Stephen. Yeah, so I think we have a couple moments here for Q&A, and I believe people can type in questions into the Q&A function. Let's give people a moment. Okay. Here's one question. How many participants can a single room handle? Tyler, you want to take that?
Yeah, I can take that one. So with a pretty bare bones ECS container without a lot of resources provisioned, we were able to get up to about 8 participants and keep it stable. For reference, a mesh topology breaks down at about 3 or 4 participants. When load testing on a beefier machine, we were able to get up to about 15 active participants. And an active participant is somebody streaming both audio and video. Again, for reference, the commercial solutions like Twilio and Agora, they support up to 17, where we were able to get up to about 15 before things started to break down. So I would say we hit the mark pretty well there. We would like to, but didn't quite get around to it, implementing a couple of other features like bitrate limiting, pagination of clients, like in Zoom, where you can see 16 people, click an arrow and see another 16 people, doing active speakers, that sort of thing. And this would help to greatly increase the overall number of participants in a single call, up to dozens or more.
Thanks, Tyler. One more question here. Why did you choose AWS for the cloud infrastructure? Stephen, why don't you take this one?
Sure. So there were two main reasons, I think. Probably the first one is just familiarity. Our team was a little bit familiar, had a little bit of experience working with AWS. And so that made it quick for us to get up and running as opposed to learning, how to use Azure or something like that. So that was one of the reasons. And the other reason is, AWS is the predominant market share in the United States. So, being able to accommodate as many users as possible means more people be able to use the application.
Great. Thanks, Stephen. No more open questions here, so I think we can wrap up. Thanks, everyone, for your time today and joining us, and have a great rest of your day.